Now, when we look at bivariate data, we like to show our data generally in a scatter plot. And a scatter plot looks something like this. Make sure you always label your axes, including labeling the units. Here, amount of water in a glass, let's put in mils, with time in days. And here we've got height in metres against weight in kilograms. Now, obviously, either of these would be related to some experiment that's been done or some study that's been examined. Now, scatter plots help us spot the associations that are between the variables. But it's super important that we know that an association does not mean that one thing causes the other. It might, but you can't tell just from a scatter plot. What you can do is you can use a scatter plot to see if there is an association between two variables. And if you find that there is, particularly if you find that there's a strong one, then you need other sorts of studies to work out what might cause something else. Because of course, two things might be caused by a third variable that you haven't actually measured, and your scatter plot won't tell you that. So make sure you never imply that one thing causes another just because they have an association. Now, the things that we want to look for when we're looking for these associations is we want to look for the shape or the form of the association. Does it look like a straight line, or perhaps a curve might describe it better? This one over here, I can see that the data points look fairly much like a straight line. This one, it's a little hard to tell. What direction is the association? As one thing increases, is the other thing also increasing? This would mean that a line of best fit that's drawn through here would have a positive gradient. As one thing goes up, the other thing goes up. Or is the direction actually negative? As one variable gets bigger, the other variable actually gets smaller. And in that case, your line of best fit that you draw through the data would actually have a negative gradient, wouldn't it? So is the line of best fit positive or negative? The strength of the association asks, well, how well aligned are these data points? Are they all in a lovely straight row and a line of best fit will go through every single one of them? Or are they sort of more loosely scattered? Now, a bunch of times I've already used this term, a line of best fit. You might have seen this before, but if you haven't, the concept of a line of best fit is that it minimises the distance between each data point and that line. So how do you draw it? Well, you can get statistical software to actually draw it for you, and it will mathematically come up with a formula for that line that automatically minimises all of those distances and gets the best possible fit. You can also draw a pretty good one by eye, and most people who have drawn a few come up with one that's really quite close to what your statistical software will come up with. So to give you an example of how to draw one by eye, here I've got a bunch of dots. If I line up a ruler going across the dots and try and get it so that some of the dots are above my line and some of them are below, and probably an even number of both, it's quite easy to move the ruler around until you're fairly happy that probably the line that you're drawing has got some dots above it and some dots below it and some dots right through it. And if you were to work out how far below or how far above each dot was and average those, now in actual fact they average the square of the distances, and that's because some of the distances will be negative and some will be positive. But for our purposes, it's enough to say we're minimising the distances between all the dots in the line, and we're making it so that it's evenly above some dots and below others. We can see there that most of the dots fit that line really well. So when we're looking at the strength of an association, I would say that this is a strong association because most of the dots are really close, they're really well aligned to my line. If I was to draw a line of best fit here, and these 2 points aren't actually in it, it's a little bit harder to do, but putting your ruler in there and trying to get your ruler so that some of the dots are above and some are below, and it's sort of averaging out the distances, I can sort of have a bit of a guess and draw something like that. Sometimes once you've drawn it, you'll go, actually that's maybe a little bit low, I should have made it a bit higher. You could perhaps correct it and draw another one. I can see here that because many of the data points are a long way from my line, the strength of this association is not nearly as strong as this one. Does that make sense? Now, we've got some formulas and some fancy maths that we can use to work out exactly how strong an association is. By eye, we can tell this one is stronger. we have Pearson's correlation coefficient. And we call this number, this fancy number, R. And when you've got a bunch of data points, you can actually calculate R using your calculator. I'll show you how to do that in a moment. You can also be given R values and need to understand what they mean. So R, or Pearson's correlation coefficient, defines the strength of an association. Basically, it describes how close, on average, the data points lie to that line of best fit. Now, these ones lie very close, these ones don't lie very close at all, so this is a stronger association than this one. All right, so here are some words that we can memorise and know. We have everything here from a perfect correlation, strong correlation, moderate, weak, or no correlation at all. And these R numbers all lie between -1 and 1. Now, a negative correlation means a negative gradient. A positive correlation means a positive gradient. So if we have a perfect correlation, it's either going to be +1 if it's a correlation that's positive, or -1 if it's going the other way. So if Pearson's correlation coefficient is R, what do various R values actually look like? Well, here I've listed some types of correlations from perfect all the way down to no correlation at all. And you'll notice that these ones all have an R value that is positive. And you'll see that generally we have positive associations here, which means as one variable goes up, the other one does too. These ones all have negative R values, and they have negative associations, which means that as one goes up, the other thing goes down. And that just means that the gradient of the line of best fit would be negative. Now, there's no hard and fast rule for exactly where the cutoffs are with what you call a strong or a moderate association. So you've got to use these words with a little bit of leeway and just use language that kind of makes sense. There's also no hard and fast rule about exactly what R value is the cutoff for describing an association a certain way. But this just gives us a basic sort of rule of thumb. A perfect correlation is going to have an R value very close to 1, and the dots are going to look like they're in pretty well a straight line. A line of best fit here is going to have all of the points not very far away from that line. So this is a strong association. It's going to have a fairly high R value, probably something around about 0.75, or if it's going the other way, -0.75. Moderate, well, you can see here there's a general trend upwards, but it's not nearly as defined as this one. Easy ways to spot it is that low values on the x-axis seem to be associated with low values on the y-axis, and there's not any values so much down in this part of the graph or up in this part, and that tells you that there must be a bit of an upward trend, but it's not a really obvious one. And a moderate association of around about 0.5 with an R value will look something like that. Same, but the other direction. And a weak association will look like the data points are even more spread out, or even further away from a potential line of best fit. No correlation at all, of course, means that it doesn't really matter if it's positive or negative. The dots don't imply anything. We can't really see that a line of best fit would be positive or negative with its gradient. So its R value is not necessarily positive or negative, it just sort of has something that's around about 0 or very close to. So if you had an R value of -0.1 or 0.1, you'd be pretty much saying, look, there's not really much correlation between those two variables.